Good evening. Happy Lunar New Year. And welcome to the first Watson Lecture of 2025. I want to thank each and every one of you for being here tonight. I want to send a special word of thanks to all of the representatives from the Division of Geological and Planetary Sciences that helped us out, and also shout out our junior Watsons that are here from Los Angeles Leadership Academy. Thank you all for being here with us. I'm Crystal Dilworth. I am a science communicator, that's what I do. I communicate very well, especially in English, apparently, and a Caltech alum, and I'm your host for this evening. Watson Lectures have been, for the last 102 years, a conduit of connection between Caltech and the population of greater Los Angeles. And we are united not just by our curiosity, but by our shared experience. And recently, the Los Angeles fires have devastated our neighborhood and our community in ways that Caltech President Tom Rosenbaum said, words are just inadequate to describe. Here at Caltech, more than 250 of our colleagues across campus and at JPL lost their homes. And more than 1,800 of us were displaced. Behind those numbers are shared stories of survival and of loss. But the same spirit of innovation and discovery that characterizes Caltech will also characterize our response to this crisis. We will continue to take care of those of us in the community that need it most. We will continue to rebuild, we will continue to innovate, and we will continue to ask challenging scientific questions that will help us process and understand all of these events. And one of the people that is asking those scientific questions is tonight's speaker, Dr. Michael Lamb. And he has so generously agreed to adjust his intended topic for tonight's lecture to tell us about some of the recent work that he and his team have been doing on debris flow, understanding why they are so common after fire, and understanding what can be done to forecast their impact. So, for tonight's program, we'll hear an introduction by the Division Chair of Geological and Planetary Sciences, Dr. John Eiler. You'll see a short video with a little bit more information about Dr. Lamb's life and work. And then after his talk, you will get a chance to get some of your questions answered. It really is the first Watson Lecture of 2025, isn't it? All right, so the way that you do that is you take out your phones and you take a picture of the QR code that will be up on the screen at that time. That will take you to the program Slido where you can submit your questions. Now, if you don't like doing it on your phone, that's totally fine. Flag down one of our friendly ushers. They'll bring a comment card. You can write down your question, and they'll make sure that it gets uploaded to the system so it can be asked on stage. We do ask, though, that you refrain from asking questions about your specific home, property, or location. You'll see why. And so, without further ado, I guess time is here to turn off your watches, your cell phones, all of your technology that makes noise. Note your nearest exits, and please help me welcome to the stage the Division Chair for Geological and Planetary Sciences, Dr. John Eiler.
Thank you all so much for being here. This is a really exciting night for me. I hope also for you. I'm delighted to be able to welcome tonight's Watson lecturer, Mike Lamb, who's been my colleague in Caltech's Division of Geological and Planetary Sciences for the last 16 years. I'm showing my age on top, him a little less so, but we've spent a lot of years together, and so I very much appreciate everything that he's brought to our campus and that he's going to bring to you tonight. This is an unusually energetic Watson Lecture night from my point of view. I don't know, you can't see yourselves, but I can see you, and you all look enthused, and lots of people were responding to this event when they heard what it was going to be about. This is also a special night because we're welcoming members of Caltech's Board of Trustees who are on campus for their annual gathering where they chart the Institute's path for the coming year. And so we should all welcome them and thank them for spending a couple of hours with us at this event. So this excitement is easy for me to understand because I know what's coming. He's not going to tell you, but because he's a good Midwesterner like myself. But Mike is actually one of the most gifted and insightful earth scientists that I know, and I know a bunch of them because that's the world that I move in. And he's going to tell you things about something that we all have experienced personally. Many of us have dramatic stories, things that we've gone through ourselves, some of them harrowing, some of them unbelievable in the last weeks. And we're going to hear from Mike, what does this look like from the perspective of somebody who studies the Earth's surface and its changes for a living? So Mike originally planned to discuss other parts of his research program, but literally in the middle of the Eaton Fire's peak, while it was still raging up in the hills, he came to my office in the GPS division buildings, and he said, John, I was thinking maybe I should, instead of talking about this thing I've been preparing to talk about for weeks or months, let's just spin on a dime and talk about this thing that is happening around us and make this a special event. And my first thought was classic Mike. So Mike is interested in and able to speak to essentially anything that happens on or to the Earth's surface. He's a proper geologist in that respect. And I'd also say this is classic Caltech, where we've long valued the idea of rolling up your sleeves and going after the heart of problems that are really impacting people's daily lives. So I'd also like to say you're going to get to see a great window on what it means to be a natural scientist in the year 2025. I'm guessing, I haven't seen it for sure, but I'm guessing Mike is going to show you data from satellites and drones and giant laboratory experiments and computer models and all this stuff. But all of this is just a complement to the human experience of walking through a landscape and contemplating deeply what you see, which is something all of us get to do, but he gets to do it with decades of training and experience and a big melon up in his head. So maybe as you listen to Mike, try to picture Charles Darwin if he'd had a radar gun and a laptop when he got on the Beagle. That's the basic idea. So now let me turn your attention to a video that was produced by the Watson Lecture team, which will introduce Mike in his own words. And I thank you and hope you enjoy your evening as much as I know I will.
We live and work next to rivers, we use them. But as a geologist, I'm also interested in how rivers have shaped the Earth over geologic time. So think of like, how did the Grand Canyon get there? We worked on the Mississippi Delta for a while. I've worked on Los Angeles and debris flows, worked on rivers on Mars, and now we're trying to understand what's happening in the Arctic. My name's Michael Lamb. I'm a professor of geology at Caltech. And my group studies geomorphology, which is how the surface of the Earth changes over time. I'm from Minnesota, which means I don't like to talk about myself. And I was an undergraduate at the University of Minnesota. I took some geology classes as electives, and it was a small class with a very energetic instructor, Christian Tessier, who was very excited about the latest knowledge that had been gained in earth science over just the last 5 or 10 years. So I set off on that track, switched my major to earth science, and then continued, and here I am. Being a faculty member here is, it's probably the best job that you could have as a geologist. Caltech's a great place for it. It's a very vibrant department. There's excited people working on all kinds of interesting problems. It's very collaborative. I work mostly with PhD students and postdoctoral scholars during the day. Like, most of my hours are spent mentoring those folks who are doing the day-to-day grind of working on these research projects, defining problems, outlining a plan to tackle those problems, and then as they start to get results, feedback and exchange about how do we put them in the right context to understand what it means and write it up for, for formal publication or presentations. Often the way that the Earth changes is so slow that we don't really recognize that it's dynamic in the way that it is. So we have this lab. It's actually called the Earth Surface Dynamics Laboratory. That's what I named it when I started here, but everyone calls it the Flume Lab. So the Flume Lab has indoor rivers in it. Think, you go to the science museum and your kids, they have like a river with sand and you play with it. It's just like that, except we do more sophisticated measurements and have a bunch of tools that we use to try to understand how rivers or landslides and debris flows work. But really, at the heart of it, the lab is a tool to speed up time so that we can see what's happening and observe it on our own time rather than waiting for the Earth to do it for us. We have to have a long-term perspective, like beyond our lifetime perspective, to understand how our actions change how the Earth works. Hi, everyone. Welcome to the Watson Lecture. Thanks for coming. As you saw in that video, my group thinks about how erosion and deposition shape the surface of the Earth. And I point you to this picture in the background. This is a beautiful image from Utah. And when I see this picture, what I see are the rocks breaking down at the surface. Let's see if I get this to work. To produce these boulders that are coming down on this cliffside. And the rain coming down and cutting these valleys through the mudstone, creating this badland landscape. And I see it like a movie, but of course, it's just a snapshot. Our lives are very short compared to geologic time, but as it was talking about in that video, the Earth is dynamic and changing, and these kinds of movies are playing out, and we get to see little snippets of it. That's one of the things that makes it fun being a geologist, is thinking about how small you are in the vastness of time of the Earth. Sometimes things change fast, though, and fires is one of those times. And that's what I want to talk to you today about. So I moved to Caltech in about 2009. That was during the station fire, just before the station fire. Now you remember, it was one of the biggest fires that we've had in the San Gabriel Mountains at that time, one of the biggest in California. There's been bigger since. And, fires burn, of course, in the mountains, the vegetated veneer of the Earth that we look at, and that's what's most obvious. But they also change the surface of the Earth itself by moving the material. The sediment, the soil, gets moved after these sort of events. And so that's where I come at this scientific problem, is trying to understand this movement of material and how that shapes the surface of the Earth. Now, of course, these movement events can be devastating to people if they're in their way. And that so happened after the station fire. For those of you that live in the La Cañada area, you may remember that one of the debris basins, of which we have many along the San Gabriel mountain front that protect us from these types of flows, one of them overspilled, came down Ocean View Boulevard in 2010, and about 40 homes were destroyed. You can see the size of mud and boulders that were moved in this event. Cars thrown about. So these can be very devastating events. Now, because I just started, I was excited as a geologist. Sometimes as geologists we feel guilty because people's houses are destroyed, but we get excited to go see them. And the reason why isn't because we want to gawk at the devastation, it's because we actually saw the tick of the geologic clock move. And that change is something that we study and we're interested to learn about. So I took my class out there, my first class, here in January of 2010. So you can see I've barely aged a bit. And this class was just a group to think about and learn about these kinds of land movement events that occur after fires. And it turned into a research program on this topic that we've worked on over the past 15 years or so. So I want to share some of that with you tonight. So that brings us to the topic of today, which is the science of these post-fire debris flows. There's a number of people to thank. Because we've been working on this for a while, there was a group that worked on the station fire. It was led by Roman DiBiase, who was a postdoctoral scholar here at the time. He's now a professor at Penn State. We worked on the fish fire, really led by Marissa Palusis, who also was a postdoctoral scholar here in my group, and now she's a professor at Dartmouth. And now we're working on the Eaton fire with Emily Guyman, a PhD student here, and Zhang Chen, who's a postdoctoral scholar. I have to acknowledge all of the government officials that are involved in this, keeping us safe. So for the Eaton fire debris flows, there are teams from the federal government, there's the USDA, there's the US Forest Service. From the state, there's the California Geological Survey and CAL FIRE who are running things. There's LA County down to your city local officials. And we work hand in hand to try to not get in these folks' way, but at the same time try to collect data that helps us learn about these events. So today I want to go through these slides with you, topics. I want to talk about what is a debris flow, why are they common after fires, and what can be done to forecast the hazards. So we're going to go through and cover this material. So first, what is a debris flow? So many of you maybe have not seen a debris flow in action. This is a video from the fish fire in Duarte in 2016. These rocks that are coming down are 6-8 feet across. So this is a tremendously violent type of event. Sometimes people call these mudslides in the media, but they're not mudslides. They're full of boulders and rock. They can move up to 15 miles per hour. They're 6 feet deep or more and move these giant boulders that you see coming through the screen. It's important just to get us all on the same page that this isn't a normal flood. You think of floods and they're water. They're mostly water, and normal floods maybe move a little bit of sand and gravel along the bottom of a riverbed, for example. This is not that. This thing is mostly rock, not water. And so that's what makes them particularly destructive. They can move deeper, faster, and be far more destructive because of all of this material. Okay, well, this is a geology class, so we're also going to learn a little bit about the geology. So as I mentioned, these kinds of debris flows, they're a hazard, but they also build the landscapes that we live and work and see. Those are easier to see when you go somewhere where people aren't living on and haven't altered the landscape. So we go to Death Valley. This is the Panamint Range. And this beautiful fan of material, of sediment, rocks, sand, and boulders that have come down here and built this landform is built mostly by debris flows. So this is debris flows' natural habitat. The debris flows come from these mountain sources. They get transported downstream, and then their deposits build these fans, these debris fans. So this is the type of landscape. If you see this, you should say, hey, that's built by debris flows. Okay, it turns out that we're in the sort of nexus of debris flow heaven here. So right in Southern California, whether you like it or not, we live where post-fire debris flows are very common, probably more common than anywhere else in the country, perhaps even in the world. These are leading scientists from the US Geological Survey, and you can read their quote up there that Southern California has a lot of post-fire debris flows. And the reason is because of really three overlapping things. So we have fire that creates loose soil. We have steep hills In fact, the San Gabriel Mountains are some of the steepest mountains that we have in the country. And we have high-intensity rainfall events. We have these atmospheric rivers that you hear about. The combination of these three things leads to debris flows. And they can be devastating. Like this one in 2018, I'm sure that you all remember the Montecito debris flows, which were some of the most deadly in the last 100 years. 23 lives lost, 500 properties destroyed, and over $500 million in direct costs. Again, look at the size of some of the rocks that are moved in these flows. Okay, this is a table of the most destructive debris flows that have happened over the last 100 years or so in the US. And you don't have to go through all of the table here. At the bottom is the Montecito event that I just talked about from 2018. But what I want you to take note of is the ones I've starred are the majority here, and the starred ones have all occurred in the San Gabriel Mountains. So it's not just that Southern California is where post-fire debris flows happen, it's here, right in front of the San Gabriel Mountains. That's the place. So I want to take you all the way back to the 1934 debris flows that happened in La Crescenta and Montrose. Those were some of the deadliest debris flows on this list. They killed 42 people, damaged about 500 homes, and it was much, much less populated in 1934. So let's have a look. Here's the front page of the LA Times. So if you're familiar with this area, this is La Crescenta, La Cañada. Christian Frankenberg's professor here sitting up here, he lives right over here, right in the middle of this debris flow. This is Foothill Boulevard. I-210 goes right through here, right, but didn't exist at this time. These debris flows came out of the mountains. They came all the way down across Foothill Boulevard and went all the way down through Montrose. So these are massive flows that went miles into the urban environment. You can see cars trapped here. Now, there was a Caltech scientist who studied this event. This is a master's thesis from Caltech, from the geology department, 1934. And these are pictures that they took. These pictures are not that dissimilar from what I just showed you from the Montecito flows that occurred 100 years later. And we're in sort of the same predicament of having houses built on these debris flow fans destroyed by these boulders. This is Honolulu Avenue all the way down into Montrose. Honolulu grocery store. Okay, so this picture should look sort of similar to you to Death Valley. It's the same sort of setup. We have mountains that are the debris flow source. These debris flows get transported downhill, and then they end up on the debris flow deposits on the fan. Except now we live on the debris flow fan. So we've entered the debris flow's natural habitat. Here's a good graphic. This is of the La Crescenta area. It's been flipped sideways. So these are the San Gabriel Mountains here. And this is from 1934. And all of these white fan-shaped features that you see here, these are the debris flows that came out during that event in 1934. So this is an aerial photograph that was taken just after the debris flows. So watch closely, and we'll have some magic of PowerPoint. So this is what this area looks like now, well, in 2018. But you can see, whoa, there's a lot of people that live here now. Well, it's cool. Let's see it again. Okay, so look at all these people live here. This is Foothill Boulevard. In fact, I live right up here. What am I doing up there? We live on debris flow deposits. And in fact, this is a picture of my front yard that I took yesterday. These are boulders. These weren't put here by a landscape architect. These were from the 1934 debris flow. It came through my property. If you have boulders in your front yard, you should wonder, how did they get there? Okay. One of the reasons we're able to live in such density, though, now is because we have engineering infrastructure that, for the most part, protects us from these debris flows. In 1934, they didn't have this. And in fact, it was the 1934 event that really inspired the Army Corps of Engineers and LA County to invest substantially in this infrastructure. And so if you live up against the mountain front, you probably live near a structure like this or a debris basin. These debris basins, there's about 100 of them that go across the front of the San Gabriel Mountains, and for the most part, they capture all of the sediment that comes off of the mountains so that it doesn't go into our neighborhoods. This is really an engineering feat, and there's not anything quite like it anywhere else in the country, meaning that all of the sediment that's eroded off the San Gabriel Mountains, one of the steepest mountain ranges that we have, is now captured by basins, rather than being transported by debris flows and rivers out across the landscape. It's captured by basins where it's moved by dump trucks. So it's really a remarkable amount of material, and it's written about nicely in this book by John McPhee, Los Angeles versus the Mountains. Okay, so I've introduced you to debris flows. Now let's get into the fires. After fires is when we really have debris flows. Can they occur without fires? Yes, and they do. But after fires, they really turn on, okay? And so what's going on? All right, a little bit more geology. We're gonna have to back up. This is a map of where we are. Here's Beckman Auditorium, where you sit. And what's colored here is the elevation, Los Angeles Basin, and this big high elevation area is the San Gabriel Mountains sitting above us. Now, the San Gabriel Mountains are there because of collision between two tectonic plates. And these tectonic plates collide along the San Andreas Fault. You can see the San Andreas Fault here. It runs along the backside, the north side of the San Gabriel Mountains. So as the plates are crunching into each other, the rocks are pushed up. And they're pushed up at a pretty good rate, about 1 inch every 50 years. Now, this isn't the rate that the Himalayas are going up. It's not a world record or anything. But for the lower 48, it's probably the fastest uplifting rocks that we have. So these rocks are going up at a pretty good clip, 1 inch per 50 years, but the mountains actually aren't raising up. So it's not like 50 years ago they were 1 inch shorter. In fact, the erosion keeps up with the uplift of the rock. So the rocks get pushed up, but then it gets broken down into sand. That sand gets moved off by debris flows. And so the mountains stay the same height. But there's a constant conveyor belt of material that's going through the mountains and being shed down to these lower elevation areas. So let me dig into this a little bit more in this idea of the soil conveyor belt. So pretend that this is a cross-section. You've taken a part of the mountain and you're looking at it now through the side. So down at depth, there's rock. And on top of the rock, there's a veneer of soil. In the San Gabriel Mountains, maybe this is pretty thin. It's not thin on the diagram, but it's only probably a few feet thick. Otherwise, the mountains are made of rock, okay? But what's happening over time is that this uplifting rock from the plates being collided, inch per 50 years, is bringing the rocks up. That rock's breaking down, and the soil turning into soil, and the soil is creeping its way down the hillside. That finds its way into the river channels, where then it gets moved on out at the same rate at 1 inch per 50 years, okay? And then because we live in the San Gabriel Mountains, it goes into a dump truck, okay? And then it gets moved out of the dump truck at the same rate. Now that ends up being a lot of dump trucks, because this is a big mountain range. About 20,000 dump trucks a year is your tax dollars at work, LA County moving sediment so that we can live in paradise like we do here. Okay, back to the fires. Every blob on here is a fire that's happened. We're clicking through 100 years of time on the San Gabriel Mountains, from 1920 in the dark blues to 2020 to the present. This area burns, and it's burned over and over again. You can see that every square foot on the San Gabriel Mountains has burned many times over. The average recurrence interval for fires is about 20 to 25 years, meaning you could pick any spot in the mountains and stand there and say, every 25 years this is going to burn. That's what's happened over the last 100 years or so. So this area is disturbed by fires. This awesome movie is from Emily Guyman. Okay, so the fires disturb this soil conveyor belt. And the reason that we know that is from the debris basin data itself. Because we have the debris basins, we have a record for 100 years of the amount of material that's come off of the mountains. And we don't have that nearly anywhere else in the world. You imagine how difficult it would be to send a group of graduate students out to measure how much sediment is coming off the entire mountain range. That's a very hard thing to do, but because of these basins, and because somebody's paying for these dump trucks, it's known how much material is being moved, okay? So this is a plot of showing how much material is being trapped in these basins versus the time since there was last a fire, okay? So when you go at 10, 20, 30, or 40 years since there's been a fire, these numbers jump up and down, but on average, they're the 1 inch per 50 years, meaning that the rate at which these plates are colliding and bringing rock up to the surface is the same rate that we are catching the material in the debris basins. It's pretty remarkable, actually. But what's going on here? In the first year or two after fire, there's a much, much higher rate of sediment and soil that's coming off of the mountains, as caught in the debris basins. So this is a logarithmic scale, so this jump here is about 20 times. So in the first year after a fire, there's 20 times more material than the background rate. 20 times more material than the plates colliding together are giving it. Okay. In dump trucks, instead of 20,000 dump trucks, there's 400,000 dump trucks worth of material in that year after the fire. That's why those dump trucks are going past your house. Okay, so fire disrupts the soil conveyor belt. They mobilize about 20 years worth of erosion in a single event. Well, how do they do this? Okay? Now, for the fifth graders that are out there, this might start to sound familiar. We've made an observation, and we've made a question. That's right, we're using the scientific method. After observation and question comes hypothesis. So I'm going to give you two hypotheses that scientists are debating about to answer this question. How exactly are fires disturbing the soil conveyor belt? So the first one is a popular one that's been around for a long time. And it's shown here in this infographic from the Washington Post. They didn't come up with it, scientists did, but it's a nice cartoon. And I'm going to call it the wet hypothesis, okay? So the wet hypothesis is that plants grow in the soil. The fire burns the plants. When it burns the plants, it can get so hot that it can actually vaporize some of the organic material. And this vaporized organic material gets into the layer of soil and creates a sort of sticky substance that makes it very hard for water to penetrate. So sometimes you'll read about this in the media and they'll say that the soil has become hydrophobic or water repellent, meaning that the water just won't sink in. So normally when it rains, the water sinks in the soil, but after fire, because it can't sink in the soil, it runs over the surface of the landscape. And when it runs over the surface, it can get going fast, and then it starts to pick up the soil, erode it, and turn into a debris flow. Okay, this is the wet hypothesis. Here's some evidence for this kind of erosion behavior. This is after the Montecito debris flow. This is Tom Dunn, a famous geologist from UC Santa Barbara. And I went out with him after Montecito to look for evidence of some of these mechanisms. So this is a soil. We're sitting on the side of the hill onto the soil here. And you can see these grooves that were cut into the soil after the rainfall. And this would be the kind of evidence that would support this wet hypothesis, meaning that the water couldn't soak into the soil, so it ran across the surface and cut these sort of grooves. And the idea is as these grooves would coalesce as you go further downstream, they could turn into one of these bigger debris flows. So let me put it into cartoon form, the wet hypothesis. First, these hills have this thick mantle of soil, thick, stable soil layer, like I showed you in the picture before. And then after it burns, the runoff creates these grooves, they come together, and somehow that transforms into a bigger debris flow. Okay, there's some problems with this hypothesis for our local mountains. And they all come down to that these mountains are very steep, as I've told you about. So this is a picture of Mount Lukens. It's from behind my house in La Crescenta, La Cañada area. And you'll see it's actually a visual image, but it's overlaid on digital topography. So the gray area is actually a digital representation from measurements of the topography. And what I've done here is I've colored all the areas that are steeper than 45 degrees. 45 degrees is very steep. 45 degrees is 100% grade if you're a trucker, right? So 45 degrees is so steep that the sand and the gravel won't stay put on 45 degrees. It will simply just roll off, okay? You don't need water, you don't need anything, it just rolls away. And that's exactly what we see when we go into these landscapes. The hillsides are extremely steep, and the hillsides lack soil, it just rolls away. This is a picture of a hillside after the station fire, and the movie is one that Emily took just last weekend out from Mount Bailey in Sierra Madre, or not Mount Bailey, from Bailey Canyon in Sierra Madre. And you can see this is before any rainfall. The hillsides don't have any soil on it. They're bare and rocky. And there's these cones of loose material, loose sand that's collected down at the bottom here. And this is the soil that used to be on the hillside. It's already come off the hillside before we've had any rain. It's so steep that it just rolls and bounces its way downslope until it finds a lower sloping area to come to rest. Usually that lower sloping area is the channel bottom or the stream bottom as it's done here. Sometimes it's a fire road. Here's a picture of a fire road after the station fire. This is a problem that the firefighters know very well because if you want to drive a fire truck up one of these roads and fight the fire, this material is raining down on you during the fire, right? It's not, again, it's a dry process, doesn't happen in the rain. This is happening as the fire is happening, making these roads hard to get through. Okay, so what's going on with this dry process? Well, Roman DiBiase, when he was a postdoc here, worked on this problem, and we figured that the plants were actually acting like little dams on these rocky slopes. So you can see a picture of Roman trying to dig up the sediment pile that was stuck behind one of these plants on a slope that's so steep that if it didn't have the sediment, if it didn't have the plant, the soil would just roll its way down the hill. But because it has a plant, there's an area where these sand and gravel and rocks get trapped behind the plant. Simple as that. We'll call it a plant dam. You burn the plant, and then there's no longer that support for this material, and it just starts coming down dry. Okay, so this is the dry hypothesis then in these sort of cartoons. So instead of having a thick layer of soil on the hillside, we just have these little patches of soil that are trapped behind the plants, these plant dams. You burn the plant dams, and that material comes down dry. Before there's any rainfall, it comes down and it ends up in the river channel. And this is something that we can see happening. So before we have any big storm events or debris flows, these channels are being loaded. The gun is loaded, so to speak, and you can see it and measure it. And then once we get the rain to come down, the sediment gets swooped out in a debris flow. But it's coming from the stream channels on the bottom rather than eroding the soils on the hillside, because the soils are already gone. Okay, so that's the dry hypothesis. Okay, so the dry hypothesis didn't tell you why debris flows form, though. So we have to ask another question here, which is, why, if I have all these cones of loose sand and gravel and rocks collecting in a stream channel, why do they turn into a debris flow? So this is from the Colby fire, where we put out a camera to capture the rains after this fire, and you can see this loose material is easily mobilized. It becomes a debris flow, and that's where most of the material that's coming out of this canyon is coming from, not from up on the hillsides, because they've already lost their soil. So how does this happen? Well, if I were to go put a few graduate students out there, they would get mad at me because they would be in the debris flow. And there's rules against that, and there's new regulations, and I've already gotten in trouble. So I don't do that anymore. Instead, we've decided to try to investigate these kind of problems in the laboratory. So the laboratory allows us, as you saw in the introductory video, sort of investigate the flow of water and sediment, make debris flows, make landslides. But we can do these things on our own time, do them in a way that we can control the variables and understand how they work without having to go out and let Mother Nature, wait for Mother Nature to do this for us. So we have this large facility. It was called a flume in the video, that's what we call it. And these are folks that have worked on this problem. Okay, so I like to put bowling balls in the flume. I don't know, there's just something about them that I like. So you put a bowling ball in the flume, and it's sitting here on the gravel, and you wonder, well, when's this bowling ball going to move? How much water is it going to take to move? And so I want to introduce you just to this simple concept that should make intuitive sense, that to move this boulder requires a certain amount of water force. And the heavier the boulder it is, the more water force I'm going to need, right? And so there's a ratio here of forces that actually ends up being very important to understanding how sediment moves in these channels. It's the water force relative to the particle weight, okay? So what we were able to do then is do a bunch of experiments in these flumes and investigate different water forces to particle weight and see when do we get these sort of water flows and when do we get debris flows. So let me show you an example. This is peering in through the side window of one of these flumes. Here's two different experiments. They're both at 17-degree slope, so it's a fairly steep mountain stream. And in the left case, you'll see that the water's going over the top of this gravel. There's a little bit of gravel moving, but it's mostly a water flow that occasionally drags a little bit of sediment or soil with it. Now, in the case in the right, all we're going to change is the size of the material. So in this case, we have this is about 1 inch gravel. And over here, I have sand. So all I'm going to do is go from the gravel to the sand. I'm going to keep the water force the same, okay? Here we have something very different. So now we have this very concentrated, fast-moving slurry of mostly rocks. This is a debris flow, and this is a water flow. And we're able to go from one to the other and see when we get which behavior. So this is a complicated diagram, but this is the result of many, many, many experiments that we were able to map out when you get debris flow behavior, when you get water transport of sediment or soil, and when no sediment moves at all. And as you might expect, as I've explained, when the water force is large relative to the particle weight, it pushes us up into the debris flow regime. When the water force is small, we might have just water transport or no motion. And it's also a function of the steepness of the river channel, or the steepness of the flume in this case, which is plotted on this axis with steeper slopes over here. Okay, so what does this all have to do with the fires and debris flows? Okay, so let me get back to it. Most of these stream channels that we have in the San Gabriel Mountains look like this when there's not a fire. Their beds are covered in boulders that might be several feet across. But I've already shown you that after fire, these plant dams liberate all this sand that comes raining down and ends up in the channel. So the fire turns these channels from looking like this boulder bed to this sand bed. So that's a huge reduction in the particle size. The water force stays the same. We have typical rainstorms every year. So even for the same type of rain event, this dramatic change in the size of the particles makes them much more mobile and basically pushes us from a regime of no motion. Usually these boulders don't move. If you go hiking up these stream channels year after year, you can find the same boulder, the same graffiti on it. But if you cover the bed with sand, then now you get pushed up into this debris flow regime. And so that's essentially how we think debris flows get started in this dry hypothesis. Okay, so let me summarize the hypotheses a little bit for you. So this is a diagram of the amount of soil we expect on the hillsides versus the steepness of the hill. So for angles less than about 30 degrees, that's a 30-degree slope for you there, the soil is stable. It's stable with or without plants. So you burn the plants, and it's still there. The soil's not going to slough off. And so these lower sloping hills is a good place for the wet hypothesis, and looks like that hill slope I showed you from Montecito, where the soil sticks around, and then it gets eroded potentially by rainfall. But when we get into hill slope angles that are steeper than 30 degrees, up to 45 degrees or so, which are very typical of the San Gabriel Mountains, then we have this region of unstable soil. It can be trapped by the plants, these plant dams, but when you lose the plant dams, it becomes unstable and rains down into the stream channels by this just dry event before there's even any rainfall. And so these are the parts of the landscape where we think the dry hypothesis is playing a role. Okay, so that's some of the science behind debris flows. I want to now get into what can be done to forecast their hazards. Okay. This is a picture of the San Gabriel Mountains behind Altadena and Sierra Madre. Here's Interstate 210, here's Eaton Canyon, and the red area is the Altadena fire perimeter, okay? So you can see, of course, the areas that have been devastated in the urban communities, but there's a large part of the mountains that have burned too, right? And it's the areas of the mountain burning that are of most concern for debris flows because that's where they start. And this sort of landscape should look similar to landscapes that I've already shown you in Death Valley and La Crescenta. That is that debris flows have a source area. They come from the steep mountain areas. They get transported downslope, and then they end up on a debris fan. And so just like in La Cañada and La Crescenta, Altadena and Sierra Madre are also built on a debris flow fan. So we are in the debris flow's natural habitat. Okay, so what can be done to forecast these hazards since we're living on the debris flow fan? First, I'm going to show you what's being done, okay? And this isn't being done by us at Caltech. This is being done by the emergency responders through the U.S. Geological Survey, really led by the California Watershed Emergency Response Team, or WERT team, and I'll refer to them again at the end. These are the folks that are going to put out the most authoritative report on where the hazards are, and you can look up your exact neighborhood and try to learn more about what's going on, okay? They have a model that's based on not either of the hypotheses I talked about, right? Those hypotheses are the science that scientists are trying to work through and think about and test, and they're not ready for showtime yet, okay? We're still trying to understand how those mechanisms work. The way that they forecast these models is instead of trying to look at the specific mechanisms of how debris flows are getting sediment, they simply are looking at what's happened in the past. So we've had debris flows that have happened in the past. I showed you some from after the station fire. There were many more debris flows than the ones that came into the urban area that were caught by the debris basins, so they didn't cause devastation, but there's data. When did those debris flows occur? How much did it rain then? How big were they? And what they found is there's 4 main variables that control how big debris flows get. They're how much of the landscape burns. This is something that's assessed by the U.S. Department of Agriculture. That report's already been done for the Eaton Canyon. There's how steep the topography is, how steep the hills are. There's the erodibility of the soil. And then there's how hard it rains. And it really matters how hard it rains, not how much it rains. So how intense are the downpours that we have? Okay, so what they do is they look at all the debris flows that have happened in the past that they have good data for. There's only about 40 of them, so it's not that many. And then regress that information against these 4 variables and to try to see, okay, now if we go to the Eaton fire, we can measure these 4 variables and try to see if the same thing, predict that the same thing that happened in the past might happen in the future. Okay, so we've taken their predictions. This is their data, not ours, but Emily has put them into these nice graphics so we can display them. So I'm going to walk through their predictions for what the forecast is. So this is the burned area again. We've divided it up into the different watersheds because each watershed has a mouth that's going to deliver sediment out onto the fan, okay? The size of these circles represent the amount of sediment, the amount of soil that we expect to come out of these watersheds for a particular rain event. So this case here that I'm showing is for a 16 millimeter per hour rain rate. So that means 0.15 inches that has to fall in 15 minutes. So this is a weird way to think about rainfall because the forecasters, you watch the news, they say we're going to get 2 inches of rain. Last weekend, we got an inch of rain or something. But we got an inch of rain over 2 or 3 days, okay? We didn't have major debris flows in the Eaton area. There were some in Palisades. Some of that rain even fell as snow, so it might have been less rain than that. So I put up here, the amount that we had last week was about 5 times lower than this threshold, okay? So this is a scenario of a rain downpour that's 5 times bigger than we saw last weekend. Can it happen? Yes. Does it regularly happen? Yes. These kinds of rain events we get on an annual basis. But has it happened yet? No. Okay? So for this particular rain event, these are the volumes of material that should come out of these canyons. And so for reference, we put this into Olympic Olympic swimming pool sizes. So these are not small amounts of material. The small circles correspond to one Olympic swimming pool, and the big circles correspond to 100 Olympic swimming pools. Okay, but don't freak out yet, okay? Because we also have these debris basins, okay? So these are the debris basins, and these are the capacity of those debris basins to hold that material, okay? And these are also in Olympic swimming pool units, okay? And you can see that for the most part, the basins are bigger than the amount of material that's supposed to come out, Okay, so that's good, that's what we want. We want to be able to capture all that material so it's not going to come down into the neighborhoods. But there are some areas of concern. For example, these places with squares don't have basins. They tend to be little areas, little watersheds that aren't going to produce huge debris flows, but they could produce small debris flows, and they don't have basins, and so people that live right in front of those areas are probably going to get a notice that says that they'll have to be aware of what's going on. There's also some of the places that have basins, but they're not particularly big. And Sierra Madre Dam is one of them. You can see even for this pretty light rainfall event, the dam is nearly the same size as the potential material that could come out. So let me put this into this bar graph that illustrates it a little better, which is what we've done here is taken the amount sediment that's going to come out of these basins and subtracted the amount that's going to be held. And so the bars that are sticking up on top, the dark brown ones, those are potential extra sediment that's not going to be captured by the basins. Whereas all the sediment that's going to be captured is represented by those tan bars that are sticking down. So for this case, 97% across the whole burn area should be captured by the basins, but there are local areas where they could see some amount coming out. Okay? Generally less than 1 Olympic swimming pool. Okay? Now, if we go to a bigger event, things get a little bit scarier, okay? So this is a bigger rainfall event. Now, this is a large storm where we have 0.4 inches, so almost a half an inch of rain has to fall in 15 minutes. This is a heavy downpour. These heavy downpours occur, though, and on average, they occur in our mountains about once per year. It might not happen this year, it might not happen next year, but it'll happen in a few years. And sometimes it happens more than once a year. So it's not for sure it's going to happen this year, but on average, it happens about once a year. So think of this about like our annual biggest rain event. That's what this is showing. And for our annual biggest rain event, these numbers jump up, right? Same problem areas, but some of these are getting into multiple swimming pool sizes now of material that's potentially not being captured by the existing infrastructure. Okay, but still don't freak out. These are the uncertainty bars. Okay? And part of the reason the uncertainty bars are so huge is because, one, there's only 40 events that we have data for from the past. So we need more data. Second is that these 4 variables that are using to do these predictions don't capture everything that you need to know to make the predictions, right? And so this is going to result in the emergency managers being extra cautious. They're going to assume the worst from these error bars, and there's probably going to be a lot of false alarms. And the reason there's a lot of false alarms is because there's a lot of uncertainty, and they want to err on the side of safety, of course. So as scientists, one of the things we're interested in is to see, well, can we reduce these error bars? How do we make these predictions more certain? And so that's something that we're working on and want to do as we go forward in the future so that in future fires and future debris flow scenarios, we have a better chance of forecasting which places are going to have problems and which ones aren't. So I want to talk about just 2 areas that we see and we're working on to try to make improvements here in these sort of forecasts. So one is what I'm calling next generation models, but these are models that would include the actual processes that I've talked about earlier in the presentation. For example, the dry hypothesis of sediment coming out of these vegetation dams and rolling down and collecting in channels, or the wet hypothesis of the soil repellency and the runoff coming over the soil and picking up soil. These exact mechanisms aren't included in the forecast that they're using now, and part of that is because we don't totally understand how all the physics works yet. And so we're working to understand that. The more we can learn about how these flows work, the more information can go in these models and the better they will be at predicting what happened. So one way of doing this, for example, I showed you this diagram before, is we can divide the landscape up into the low gradient hills where the wet hypothesis applies and the steep hills where the dry hypothesis applies. Most of our landscape, I mentioned, falls under the dry case, so I'm going to work that forward. So once we have this dry sediment after the fire, we can route it down the hill. It just rolls and bounces down the hill. It can't be that difficult to figure out. We have the sediment rolling and bouncing down the hill and collecting in the stream channels by this dry process before there's even any rain. And then we can use some of the physics that we've learned about with the water force and the particle weight to predict where these areas are going to be mobilized to turn into debris flows, or are they going to be transported by this water flows instead of the dangerous debris flows. So Emily's already started to do this for the Eaton fire, and these are some of the inputs that go into this prediction. So first we have to know how much sediment is stored by these plant dams on the hillsides, and that depends on how long it's been since there was a fire last. Because after a fire, everything is stripped away. So then plants grow back, but it's really not the plants growing back that we care about for the dry hypothesis, it's the rebuilding of these sediment reservoirs behind the plants. And that takes time because that involves breaking the rock down and producing sediment. It tends to take about 20 or 30 years for these sediment dams to get back to their original state. You can see that these are the years since these areas in the Eaton fire burned last. And most of them burned longer than 20 or 30 years ago. In fact, this was a little pocket of the San Gabriel Mountains that hadn't burned for quite some time. So that means that there's probably a lot of sediment up there, right? It's been stored there for a while. So the next thing we do is route that material down the hill and see where it ends up. Is it going to collect on a fire road? Is it going to end up in the stream channels? And what this graphic is showing in the dark blue is all the places that have been loaded with this dry material. And it's a lot. And they're kind of everywhere in all the little steep creeks that are along the mountain front. And then the next thing we can do is do the water force to particle weight to predict, is this material going to be flushed out as a water flow, or is it going to be flushed out as a debris flow? So this is a zoom in on a little, on part of this drainage here, where you see here, and what's being shown here in the color are these collections of the dry material. And if it's blue, it's going to be transported by just the water transport. And if it's red, it would be debris flow. And then it'll go up through different rainfall rates here, starting at low rainfall rates and going up. And you'll see that as we get to higher and higher downpours, more and more of that will be mobilized as debris flows. Okay. Well, the good thing is that so far, this model that's using the dry hypothesis, including the mechanisms of having sediment roll down the hill, collect in the channels, and be flushed out, following the physics that we think is going on, actually agrees pretty well with the U.S. Geological Survey's model that is based on what happened in the past that's being used for your forecasts. And this is a comparison of that. So this is the USGS predictions. Each one of these dots represents one of these watersheds that we talked about earlier. And on the x-axis here is the amount that we would predict from the dry soil model. And there's pretty good agreement. And that suggests that, perhaps this dry soil model is accounting for much of the material that does come out of the mountains. And if that's the case, that gives us some more faith, perhaps lowering the error bars, building our confidence that these forecasts are getting the physics right. Okay, a third thing that we're doing to try to better understand and forecast these hazards is forget about the models. Why can't we just go measure it? And that's something that we can do. So in the dry hypothesis, again, I told you, right after fire, these channels are loaded with this dry material. And sometimes they're loaded with 3, 4, 5 feet. I was just talking with the head of CAL FIRE who was up in some of the mountains, and he said, there's areas of the channel beds that have 10 feet of sand that have buried the riverbed. So this is the material that's the most easy to mobilize and is going to be flushed out of the system one way or the other. But we can measure 10 feet of elevation change, and we can measure it quite precisely if we're able to get airborne laser altimetry. So this is where an airplane flies over the landscape. It has a laser, it measures the elevation of the ground. And one of these surveys was done actually just a few years ago over the San Gabriel Mountains. And one was done by CAL FIRE and the California Geological Survey right after the fire in the days following it. And so by differencing these two surveys, you can measure this accumulation and then see which catchments, which watersheds are likely to produce the biggest debris flows, because you can already measure the loose material that's in these watersheds before the rain hits. This is something that we test bedded for the station fire. What you're looking down on here is, again, a digital elevation representation of part of the watershed. This is near Brown Mountain up by JPL. And what I'm going to flip to now is showing you a difference map of what happened. This is the map before the fire. We're going to subtract the map from after the fire, and this is what you see. Those red areas are areas that have gone up in elevation by something like 1/2 to 3 meters, so 5 to 9 feet. And that's outlining the river network that you see. So the river networks are loaded, sometimes higher than me, with loose sand. And you can measure it in these difference maps. And then after it rained during this time, there was another survey done. And what you can see when you difference the later survey after the rain from this survey is that all of these go down. Now the blue is erosion, so that material that built up 6 to 10 feet now got all removed. And that removal of the material was the creation of the debris flows during the station fire. So let me illustrate this with a little cross-section. We're going to just take a little cross-section through this gully right here, and you can see it again. Here, these are the points taken from the airplane measuring the topography or the elevation of the surface. And here's one of these little river channels. And the black points are before the fire. The red points are immediately after the fire, before any rain. This is just all this dry sediment loading of the channel. And then after the rain, all that material is swept out all the way down to the blue. And so this is a lot of material between the red and the blue that gets flushed out. That's the big question that we're trying to model and predict. Where is that material? And you can measure it from the red survey that can be done before the rain happens and before the debris flow happens. So we're trying to do this now for the Eaton fire, also at even higher resolution, but now using drones that are carrying the same kind of technology. This is being led by Zhang Chen, a postdoc in our department, and Emily Guyman again. And here's pictures again from the areas just above Sierra Madre, where you can see all of this fresh sand making these cones. That material is ready to go. Okay. So I've covered most of the material I want to cover, but I want to leave you with a few closing thoughts here. So one is, well, what can you do about it? Well, there's a lot of people working overtime to try to do it for you at this point. One thing is to be aware. So I've talked to you about this dry mechanism, and I think one of the most useful things about the dry mechanism operating is that you can see where the loose material is before the debris flows happen. That means that you can be aware of what's going to happen. If this is your backyard and it looks like this material is going to come down, and it doesn't take a big rainfall event for that to happen. So this is after the Colby fire, and this was just a little bit of rain, and it flushed through. Here's a person for scale here. It's hard to get a sense of how big this is. This isn't a big one, but this certainly, could do some damage. So be aware of what the hillsides look like. If you see a big pile of loose material, that's where these things are going to come from. The second is these debris basins. These debris basins are lifesavers. And as I've said, most of our catchments, especially the big ones, have debris basins. And LA County is working overtime. I was out there just the other day and seeing people clean out the debris basins even after the light rain that we had this weekend, which didn't produce much sediment movement in our area, but nonetheless, they're keeping these as clean as they can so they can maximize their capacity. So when the dump trucks go by, go and give those people a high five or something, because this is the price that we pay to live in paradise like we do here. And so we need to keep these cleaned out, and they're busy at work doing this. You should know where these debris basins are. Do you live right downslope of a debris basin that could potentially overflow? Do you live to the sides of them? These debris flows run downhill. So be aware of your surroundings. But in general, the debris basins do a good job. So the third is areas where they're concerned about that could potentially have debris basins that overspill, or places that don't have debris basins at all, which there are some locations that are small that I mentioned. Often they'll come in with these K-rails, these concrete barriers or sandbags. These can work okay, if it's muddy water, but they're not going to do much for the debris flow like the movie I showed you where it's moving, car-sized boulders. And cars are easy to move. They're filled with air. Boulders are filled with rock. So boulders are much more difficult to move than cars, and they're regularly moved by these flows. So in a big debris flow event, as occurred during the overspill in La Cañada down Ocean View Boulevard, these K-rails were just picked up and flung around. So just be aware that putting sandbags in front of your house might keep some muddy water out, but if you're told that there's going to be big debris flows, you need to heed those type of warnings. Which brings me to the end. I'm, of course, not an emergency manager. I'm a scientist. We're trying to communicate with those folks to give them our ideas and some of our predictions, but they're the ones in charge. And as I mentioned, it's really the California Watershed Emergency Response Team that oversees the whole effort on behalf of the federal agencies that are involved, as well as the local and city officials that are involved. These people are the ones in charge. And if you go to their webpage, they have recent burned watershed assessments. And the one for the Eaton Fire is going to come out very soon. The one for the Palisades Fire came out today, I saw it. And the Eaton Fire, I've been talking with the chief here, and he said it's pending in the next day or two. So I'm not sure if it's going to be up there right now, but it'll be soon. And that's the place to go get the authoritative information about what's happening in my neighborhood and am I in an area that's at risk. All right, with that, I want to come back to thank the team of people that have been involved in this science and research. Special thanks to Emily Guyman, who's really helped me pull this work together from collecting data 3 days ago to processing it and getting it into a Watson lecture. It might be the fastest science that I've ever done. As well as let me thank all the other graduate students, postdocs, undergraduates, and staff members involved in this work. And here's some names of the different agencies of people that I've been talking about who've also been able to get us into these areas, get us permission to collect samples, and get us the latest data. So it's really a partnership with them that's made it all possible. With that, I'm going to answer questions between two ferns. So thank you.
All right, you can submit your questions. Please. Between two olive trees, I think we are. Okay, Mike.
Yes.
Why would an acknowledged world expert in debris flows choose to live in a house on a debris flow fan? Help me understand.
Well, it's a good question. There are houses that I wouldn't buy. We just moved into this area in La Cañada about 3 years ago. So I already knew a lot of this material. We live in the area that was hit by the 1934 debris flows, as I said, and the debris flows did come through that, right through our property, and probably did lay those boulders down. But that said, 1934 was before they had the debris basin infrastructure. And now there are debris basins there, and I feel good about those debris basins.
So the answer is great confidence in the Army Corps of Engineers.
And LA County are the ones who manage it, yeah. Mm-hmm.
All right, well, at least you made me feel better about living in Pasadena. Wow, we have a lot of questions here. But I think one of the things that I was wondering while listening to your talk is, how is climate change impacting these data? Like, we're showing historical data, but are we seeing changes happening more rapidly? Tell me a little bit about that.
It's a good question. I think it's one that we haven't quite figured out how, whether these debris flow hazards will be increased or not with climate change projections. So most of the projections surrounding the changing weather patterns in our area predict that we could see more intense rainfall and more prolonged periods of drought. So, of course, the more prolonged periods of drought lead to more fires, could lead to more fires. We have fires pretty frequently already. They could be more frequent. I think the question is whether that will lead to more debris flows or not. And that sort of depends on the wet hypothesis versus the dry hypothesis. Because the wet hypothesis has the hillsides with plenty of soil, And the more you burn them and the more you rain on them, the more material is going to come out. It's an inexhaustible supply. But the dry hypothesis has a limited amount of soil that's trapped behind the plants. And if you say that we have a fire in the Eaton fire zone again next year, well, there might be very little sediment to release because it all may come out this year. Then it takes time to build back up those sediment reservoirs. So I think the increased precipitation and increased fire hazards could lead to more debris flows in some settings where you have this thick soil, but in other areas where you don't have much soil, it's possible that it'll have more of a muted response.
Well, that's good.
Yeah.
My favorite question on this list right now is, where are the trucks going? Where is all of the debris going?
That's a great question because it's a mystery to me. I think, some of it gets sold for aggregate, to make concrete and use as sand. But it's a hard problem because when the sediment comes out of the mountain range, it's everything from boulders to mud. And it's expensive to sort that material into the sizes that you would want to use for construction. So there's experts here in the room that know more about it than I do. But my understanding is that a lot of it is not economical to sort and use that way. So it often gets put in areas just to store. Sometimes it's close to the debris basins, sometimes it gets trucked further out. One thing that it doesn't do is make it to the ocean, which it used to do, so these problems are connected, you hear about beach erosion along Santa Monica or along our coasts. Well, the sand that used to supply the beaches was the San Gabriel Mountain sand that was delivered to those areas. But that doesn't happen anymore. So it's a connected problem of we shut off the sediment here because we don't want to have the hazards where we live, but then you don't get the sediment going down to the beaches and areas where it would naturally sort out and the gravel would be left behind and the sand would make it farther and make it to the beaches.
I've really appreciated the way that you sort of articulated this system, and I don't think I've heard the material presented in quite this way before. What does the media commonly get wrong when they're reporting on these types of phenomena? Okay, maybe I should have asked what they get right, but if you can summarize.
Well, I think, there is a sense that we get a little bit lulled into safety living behind these debris basins because actually these debris flows are occurring much more regularly than you know about because if it's only when a debris basin gets overtopped that you hear about it in the news because then it goes into the urban environment. But the debris flows are happening quite regularly, probably many each year during heavy rainfall. And certainly in the burn zones, they happen frequently. But they're all being captured more or less by the debris basins, and they don't make the news, so we don't hear about them. When they do overspill a debris basin, often the big boulders can get stuck in the basin, and the muddy water can go over the top. And that can lead people to think that these debris flows are muddy water. And I think that's commonly said in the media that, watch out for the mudslides, or watch out for the mud flows, or, there's going to be a bunch of mud that's going to come down into your yard. But as I showed you in those videos, these things are moving huge boulders, and I don't think that, calling them muddy water doesn't convey the hazard. But in some ways, the hazard has changed for us because we're living in this engineered environment, and that's when it does overtop, it's just the muddy water on the top of the basin that comes out, not the big boulders that get stuck there.
So we've talked about fire, we've talked about debris flow. So how do earthquakes impact this system?
Oh, good question. Earthquakes shake up the mountains, and it's pretty common that you get more landslides after you have big earthquakes because it makes the soil loose, just kind of like we were talking about with the fire. And so we didn't talk about landslides and you'd say, well, what's the difference between a landslide and a debris flow? I mean, landslides are what it sounds like the land has slid down the slope, but these debris flows are these big turbulent mixtures of boulders and rock that go long distances. We do have landslides, that happen, and sometimes they interface with people and homes and can be dangerous. landslides tend to be higher after earthquakes, and sometimes they trigger debris flows on their own, even without fires.
I have a big question for you. Are you ready?
Okay, we have some water.
Based on your study of geology, do you have a prediction for which areas, for example, cities, countries, will fare best in the context of global warming? I had to ask. I want to know. Where should I move, Mike?
You know, it's a little bit outside of my zone of expertise, so I don't. But, you know, I tend to like it here.
I do too.
You know, it's nice. It's a little smoky sometimes in the debris flows, but we're handling it, I think.
We're standing on the results of a debris flow, no?
Yeah, I don't know. It's a good question. I mean, there's certainly concern about, you know, of course, whether or not there's increased debris flows after fires, increased fires is bad news, right? And especially when we have devastating fires like the ones that we had, and those sort of fires are seeming to be more and more common, you know, not just in Southern California, but throughout the state and throughout the West. You know, at the same time, there's other hazards that have increased in other parts of the country, hurricanes and this sort of thing. So I'm from Minnesota, and, you know, people aren't complaining that much about warming there.
Yet. Well, what is next then for debris flow science? Are there new technologies that will be applied? Is it taking the hypotheses that you presented to us tonight and translating them into something that's applicable for the government agencies to use for prediction? Sort of tell me a little bit about the future.
Yeah, well, I talked about a few of them that, I mean, I do think that there's a way to incorporate some of this new knowledge about, for example, the different hypotheses I talked about, how the sediment is actually moving and the physics behind that into these models. That's something that we're working on. There's this, you know, measuring with the airborne laser scanning of the Earth's elevation to try to predict and measure where the debris flows are going to occur from this dry loading before they happen. So I think those are two promising areas that people are working on, including our group. One area I didn't talk about, but wasn't shown on any of our maps, was where are these debris flows going to go? If they overspill these dams or the places that don't have debris dams, where do they go? All I showed you was the volumes that could come out of the catchments. And this is something that I know different scientists and government agencies are working on, but it's a hard problem. How do these debris flows interact with an urban environment? Most of the time where we've studied them in the past has been out in nature, out like in Death Valley, and there they're free to spread out and go where they go. But in our environment, they have streets and houses and buildings and canals and all kinds of infrastructure that they could consume or they could be diverted by and interact with. And understanding how the physics of all that works, I think, is something that folks are just starting to get a handle on.
Are there new approaches, building materials, building patterns in terms of how cities are laid out that are being examined now?
I don't know. Yeah.
I'd be very interested.
I mean, as we go back here, along the San Gabriel front is one of the most engineered environments to protect for debris flows that I know about in the U.S. And those design plans go back 100 years, right? So that was done a long time ago. That was done before we knew there was plate tectonics, before they knew that the plates were colliding and the mountains were going up at an inch every 50 years. So there's a lot that we know now that folks didn't know then. And I'm not an urban planner, so I don't know enough about how the civil engineering was done then, whether it would be done totally different if it could be done now. But I know it would be much, much more expensive.
I'm sure. Keeping on the topic of sort of engineering solutions, are there any efforts to plant fire-resistant plants or different types of foliage to kind of help create these plant dams, or are we not relying on plants for the solution?
Well, as far as I know, there isn't much going on in terms of actually trying to engineer the, the plants or what's going on into the mountains. The plant dams are a bit, coming back to like the fire frequency, you can imagine if you had plants that burned regularly, you would always then have these plant dams have a minimal amount of material, right? If we had fires that burn the whole mountain range every year, I'm not advocating for that, but if we did, we probably wouldn't have much of a debris flow problem. It's really the intermittency of the fires that creates the debris flow problem, because then the sediment is allowed to accumulate and then come out in these pulses. And so if you were to have something that was more regular, then you wouldn't have as much of a debris flow problem. So you'd have other problems because you'd have fires every year. So.
But controlled fires would be one way of sort of addressing some of these concerns.
Yeah, it's possible.
You mentioned briefly studying rivers on Mars. Would you expect to see similar behaviors on other planets?
I mean, one of the most exciting things about Mars is that we do see all kinds of familiar landscapes. So that's one of the reasons I got excited about studying Mars when planetary science developed rovers and satellites to go around Mars and started taking pictures that were high enough resolution that we could really see what's there on the planet. We realized we're like, oh, this looks just like the San Gabriel Mountains, or this looks just like the Mississippi River. And so I'm really a geologist who studies the Earth, but the similarity to some of the landscapes that we see on Mars is just striking. And so that's what has intrigued me. And it forces you to ask different questions because, for example, on Mars, I said it looks like the Mississippi River, but there's no rivers on Mars today. It's very dry, but it leaves behind the landforms that rivers create. And that's one of the cool things about being a geologist is you can be a sleuth and go out and say like, well, I recognize these landforms. Those are from a river. How big of a river was it? When did it exist? What was it like? What was the surface environment like? And so trying to piece together what happened, deep in time in Earth or on other planets through this sort of record that they leave behind in the landforms is one of the fun things about the job.
Are you using GIS tools or models?
We do, yep. Yeah, all of these maps that were made with these GIS, Geographic Information Systems tools, which is software to visualize, the Earth and the landscapes in these digital ways.
I have to ask this question because Preston's trying to solve our problems. He wants to know why we can't make a pathway for the debris to flow to the ocean and just close that loop that we have disrupted.
Yeah, it's a great question. So, because the reason is because as you go out towards the ocean, the landscape is flat. And when you're up against the mountain, the landscape is steep. And that's just the natural way that these debris fans and rivers develop. So, if you go out to Santa Monica or you go out to the beach, the areas are mostly flat. And so as the debris flows are going downhill, they're going to be able to go fast and carry a lot of material on the steep parts up against the mountains. But as the ground flattens out beneath them, then they're going to lose the energy and lose the ability to move all that material and start depositing that material out. And that's why we're on the debris flow deposits or the river deposits. So they just won't make it all the way, and if we let them go, then they will be depositing material all the way along the LA River system, and then the river, the water, so the debris flows aren't going to make it all the way to Santa Monica, but the water floods, then instead of being contained within the canals that we've engineered for them, are going to find their way across all of the neighborhoods of LA because the canals are going to be filled with the sand that's being deposited out over time because the water is going to lose its ability to carry that sand as it flattens out. So that's ultimately the problem, and the solution that the engineers came up with 100 years ago was trap all the sediment and just let the water go. And so that's why our river, LA River system, is the beautiful urban river that it is because it's been made to convey the water, but not any of the sediment. And without sediment, you don't have nice meandering forms, you don't have plants, you don't have fish, and there's some sections of the LA River that are coming back and getting a little bit of that, but inevitably if you let all the sediment from the mountains go that way, it would be so much sediment it would fill everything in, and over time that would increase the hazards that we have.
How big was the debris flow that brought down the sediments that we're standing on here, Caltech in Pasadena?
So there are probably all kinds of debris flows of all different sizes that are here, but they were built up over long periods of time. So the San Gabriel Mountains are about 5 million years old. So you have 5 million years, a long time. Geologically, that's not that long, actually. But to you and I, 5 million years is a long time.
It's a long time to be in grad school.
So these debris flow fans, like when I showed the debris flow fan in Death Valley, that wasn't deposited by one debris flow. Probably thousands, hundreds of thousands of debris flow deposits have built up and built that fan over time. So that's the same thing here. There's a very thick sequence. If you dig down to dig a foundation under these buildings, you're not hitting rock for a long, long way because there's a huge thickness, of material that's accumulated here over time.
Well, thank you so much for sharing your work on debris flow with us. Everyone, please join me in thanking Dr. Lamb for his time.
Thank you.